We've looked at vaporization and condensation and learned a bit about the energy associated with those phase changes, which occur between the liquid and gas phase. Now let's examine the phase changes between the liquid and solid phase. These would be melting and freezing. The particles in a solid have very little kinetic energy. Apart from vibrating a little bit in place, the particles don't move with respect to one another. They are fixed in a position that maximizes their interactions with one another. If sufficient heat energy is provided, they begin to move and wiggle enough to break free from the fixed positions and enter the liquid phase, where they continue to interact, but while moving fluidly around one another. As heat is added to a solid, its temperature increases. Once we reach the melting point, more heat will not go towards raising the temperature of the solid. It will go towards overcoming the interactions between the particles, and the temperature will remain constant through the process of melting. Once completely melted, additional heat will once again go back to raising the temperature of the substance. If we were to isolate a substance at its melting point, there would be an equilibrium between the liquid and solid phases. This means that freezing and melting would be occurring at equal rates. This specific temperature, where the two processes are balanced, is called the melting point of the solid or the freezing point of the liquid. These refer to the same temperature, but we would use one over the other to indicate a specific direction for the transition. Just like the energy of vaporization, we can quantify the energy needed to melt a solid. This is called the enthalpy of fusion. The precise value for the enthalpy of fusion will depend on how strongly the particles are interacting with one another in a crystalline solid. If these interactions are weak, it will result in a low melting point. If they are strong, it will be a high melting point. For water, the enthalpy of fusion is about 6 kilojoules per mole. That means it will take 6 kilojoules of energy to melt 1 mole of ice, making this an endothermic process. And likewise, 6 moles of energy will be released when 1 mole of liquid water freezes, making this an exothermic process. And now we understand the enthalpy associated with transitions between the solid and liquid phase, as well as the liquid and gas phase.